Okay, so sorry about that. So today's lecture 12. Friday will be the last lecture because the final exam for Stanford is next week. There's a fifth homework posted. That's the final homework. Today we're just going to get through more of chapter 5 and then finish it up next time and also start chapter 8. So as I mentioned, there's another homework posted for the students at Stanford that will be due next week. Their midterm is next Thursday, so the plan for next week for them would just be to review on Tuesday and give the last day. So again, this Friday will be our last day. So I want to get through more of chapter 5 today. It's called Alternative Techniques. Last time I went through the ROC curve, so I'm not going to go through that again. I just want to make a note that if you looked at the slide from last time, the true positive rate and false positive rate were written down incorrectly. They had the correct numerator, but the denominator is, so true positive rate is the true positives. The denominator on the true positive rates are basically the total number of positives that you have in your data. So everything that's a positive is either classified as such, in which case it's a true positive, or classified as a negative, in which case it's a false negative, right? And then same thing with the false positive rate when you're making the ROC curve. The numerator is the number of false positives, obviously, but the denominator is the total number of negatives in your data. So negatives are either incorrectly classified, in which case they're false positives, or they're correctly classified, in which case they're true negatives. So this denominator is the total number of positives in your data. This denominator is the total number of negatives in your data. So those never change. As you're making your ROC curve and you're going from left to right, this always is the number of positives in your data. This is always the number of negatives in your data. Those never change. The only thing that changes as you're making the ROC curve is the numerator. As you increase the number of positives that you classify, this goes up and this goes up. The whole point is you want this one to go up quickly and this one to go up slowly, so that when you make your ROC curve and you plot the true positive rate on the y-axis and the false positive rate on the x-axis, you want to go up before you go over, right? Eventually, you're going to end at the point 1, 1, but on the way there, you want to stay above the diagonal and go up faster than you go over at the beginning. Okay, so we talked about that last time, and we went through an example. Again, the diagonal represents random guessing, right? If I just say, okay, flip a biased coin, right? 40% of everything is called a positive. Well, then this thing is going to be 40%, and this thing is going to be 40%. I'm going to be right there on the diagonal at 0.4, 0.4. And there's nothing special about 40%. You could do it for any constant value. If these two things come out the same, that's just random guessing. A good classifier, we want to be in the upper left of the plot. Of course, the perfect classifier would go straight up and then shoot straight over. These are useful for comparing two classifiers, again, for a range of values. You want the classifier that lies on top, and the area under the curve. If you have to pick one single metric from the ROC curve, sometimes people literally look at the area under the curve. Of course, a perfect classifier would have area of 1.0. Random guessing would have an area of 0.50. We went through this example last time. Now, the thing I'll point out in this example, the classifiers actually give out probability estimates. So we order them based on the probability estimates for making the ROC curve. So this first observation, if this classifier M1 had to pick one observation to be classified as the positive class, it would pick this first one because 0.73 is the highest. Now, you don't actually need probability estimates to do the ROC curve. You just need sort of any ordering of these in terms of confidence, right? So these could be sort of any ordering. We'll talk about, like in boosting, it could be that the F measure. For support vector machines, it could be the distance from the margin. Any sort of ordering in terms of confidence you could use to make your ROC curve. They don't have to necessarily be probability estimates. You just have to order your estimates in terms of your confidence. And then we went through this exercise last time. So I just wanted to review that. Today, what we're going to talk about are some of these additional methods for doing classification talked about in Chapter 5. So again, Chapter 4 was all about decision trees, and I said that was just one example, not a particularly modern or effective technique, but sort of a starting point. The techniques we're going to talk about in this chapter, nearest neighbor, just because it's a very simple algorithm and you often like to consider that as a baseline for comparison. We'll talk about support vector machines today, and then tomorrow I'll start talking, Friday I'll start talking about bagging, random forest, and boosting, which your book classifies under this general category of ensemble techniques. And that is sort of a correct characterization, although arguably boosting differs a lot from random forest and bagging. So we'll talk about those next time, but today I want to get through nearest neighbor and support vector machines. So the nearest neighbor classifier is sort of an obvious thing to try. The main thing you need to have for nearest neighbor is you need to have some notion of distances between your attributes. Now, if the attributes are all numeric and they're all sort of on the same scale, obviously you could use Euclidean distance. Now, if they're not numeric, if you have categorical attributes or even ordinal attributes, you have to sort of be a little bit more creative about how you're going to define distances. And actually, there's section 2.4 in the text has a very long section where it talks about how to measure distances between attributes. The example we're going to look at, of course, is the sonar data set where everything is numeric. All 60 of the attributes are numeric, and we can just use Euclidean distance. But in general, a lot of effort goes into sort of how am I going to define distances. But once you have a notion of distance, you can use nearest neighbor classifiers. The k nearest neighbor classifier, basically, you classify a point according to the majority of the k closest training points, right? So suppose I have this new point x, right? This is a point for which I want a classification. Well, I look in my training data and I find the closest point to it. Closest point to it is this point, which is negative, so I call the point negative. That would be the one nearest neighbor. Just for every point that you want to classify, find the closest point in your training data. Sort of the most obvious thing you could do. Two nearest neighbors, you look at the two closest points, take the majority vote. Well, it's 50-50, so actually it doesn't matter. You might as well flip a coin on that one. And that's actually what the software will do. When you get a even k and it's an even number of votes in either direction and you're using a 0.5 threshold, it actually does randomization, which is kind of annoying because then your classification is non-deterministic and you run it the next time and you get a different answer. So anyway, that's sort of the default, is to do a coin flip there. And then three nearest neighbors, well, these are the three closest points. So you say, well, 2/3 of them are plus, so this point would get classified as plus. Now you could say, well, shouldn't I weight this one closer or this one more because it's closer? Some algorithms do, but by default, k nearest neighbor just takes the k closest points and does a majority vote on those. Other nearest neighbor methods you'll see will actually, instead of taking a fixed number of neighbors, take a fixed radius or something like that. But the most simple thing here is to just look at the 1, 2, 3, or in general k nearest neighbors and take a majority vote. Now some things to say, well, here's a picture. I actually made this picture in R. This, of course, is a picture of the one nearest neighbor classifier. And it's sort of interesting to see like these 2 points here, right? So I'm classifying everything that's closest to a yellow point as light blue, and everything that's closest to a black point as purple. So all the points on this line, right, they're equidistant from these 2 points. Then as I turn the corner here, this line is equidistant from these 2 points. Then here, I start to become closer to this point or closer to this point. So you sort of see, this is the neighborhood that this yellow point gets. It gets cut off there, of course, because the black point then starts to occupy some space. And you can sort of trace these guys all around. And I made the resolution pretty high on this, so it looks like, nice smooth boundaries. So that's the nearest neighbor one classifier. Now, in a two-dimensional problem, no problem. It's, pretty easy to use a classifier like this. However, these things really break down when the dimensionality is large. They really suffer from the curse of dimensionality. So sort of in high dimensions, right, every point is far away. So you often have to do some sort of variable selection first if you want this algorithm to work, or you just sort of have to hope that you've filled up your space. But to fill up a high dimensional space, the number of points you need a lot, okay? So the scales are important, okay? By that, in this picture, it's perfect, right? x1 lives on 0, 1, x2 lives on 0, 1. The space is sort of evenly filled up. However, you can imagine if x1 lives on 0, 1, but x2 lives on 0.001, then the x1 is going to dominate the distance metric. So what people generally do in that case is to scale all the numeric attributes to have equal variance, because you don't want to just have one variable dominating the distance metric just because it has a larger variation. So a common thing to do is to scale all these so they have equal variance. In the sonar data, which we're going to look at, it's not a big problem because they're already scaled to live on 0, 1, so it works well. K and n, k nearest neighbor, is the R function. It's in the library class, and it does k nearest neighbor using Euclidean distance by default, which means, of course, if you start to give it attributes which are not numeric, then it's going to do something probably pretty silly with them. But by default, it's just going to use Euclidean distance for numeric attributes. So we can look at it for the sonar data. Again, I have the test and training split, which I'll just use that. And here's how I would do this, right? So again, install.packages class will install the class package, library class. Then I read in the training data. Again, I have to make sure I'm trying to predict the 61st column, right? If you remember the sonar data, it's the 61st column that is the class label. So I'm trying to predict that using the other 60 columns. So let's see, here's the training data for sonar. So you have all these 60 numeric attributes, and then you get to the 61st column, and that's your class variable, which you're trying to predict. So I make sure that one is a factor, so R knows that it's a categorical variable and not numeric. The training data is the other 60 columns. And now here, this is sort of silly what I'm doing. I'm just trying to compute the error on the training data. So the function KNN takes 3 arguments. It takes your training data, your test data, and then the Y labels for the training data. So if I make the training data and the test data the same, both the training data and the test data, I give it the training data, it's just going to give me the fit for the training data. And actually, because the default for this thing is 1 nearest neighbor, and because all values in the sonar X data are unique, but I know this thing is going to come out to be 0. I know nearest neighbor 1 is going to give me a perfect fit on the training data. Why? Because every point is its own closest neighbor. And so just so you can see here what R is doing with the KNN function, let me show you. So help KNN. Oops. Oh, I need to read in the library. OK. Try that. So by default, again, it's doing 1 nearest neighbor. Here you can see I give it arguments training data. This is the X values for training data. Test data, this is the X values for training data. I tell it the labels, right? CL is the factor of true classes for the training data. So those are the Ys for the training data. K equal 1 is the default. And then you see some of the other things there. So that's what it's doing. And so if I make both of these the training data, then it's going to give me the predictions for the training data, which by default, 1 nearest neighbor, it's going to do a perfect job, again, because every point is its own closest neighbor. The only way this wouldn't give me 0 misclassification error on the training data would be if I had duplicate X values with different Y labels, right? Because then it would have to pick, and it would pick some of them incorrectly. But in this case, every point is its own closest neighbor. Every point is unique. So of course, this thing is going to give me 0 misclassification error on the training data, right? Which is no big deal, right? It's easy to fit the training data perfectly. In this case, it's sort of a trivial way to do it. Just say every point gets its own label, right? So this way, I have 0 misclassification on the training data. Of course, that's not at all what I care about. What I really want to know is how well it does on the test data, the data that it hasn't seen before. So now I read in the test data. Now I do KNN. X is the training data. X test is the data that I want the predictions for, and of course Y is still the training labels. And so now I'm going to look at where does Y test equal the fit? What's the fit? The fit is this thing. Y test, of course, is the labels from the test data. And so where are these equal? Take the sum of that, divide by the total number of observations, 1 minus that. That, of course, is the error on the test data. Now, if you remember last time we used the trees from our part, and we got about a 30% misclassification error. Actually, we got down to like 27 or 28. This guy, oh, I'll just ask. Anyone know off the top of your head, nearest neighbor 1 on sonar data? No? OK. Just thought I'd ask. It's about 20%. There you go, 20.5. Let's call it 21%. So for sonar data, nearest neighbor 1 gives you about 79% accuracy or 21% misclassification error. And some people generally use this as some sort of a benchmark because it's such a simple procedure. If you have all numeric attributes, I would be curious to know what does nearest neighbor 1 do for your data set. And here it's about 21%. So if you write a paper and you say, oh, I have this great classification technique, it does really well on this data set, it has 79% accuracy or whatever. Well, let me compare it to nearest neighbor 1, which is maybe the simplest thing I could do, and see how well that does. So that is nearest neighbor 1 on the sonar data set. And let's see, yeah, I did all that. So I think that's all I wanted to say about it. The only reason I really wanted to mention this nearest neighbor classifier is because it is a simple technique, and it's often something I want to consider as a competitor to sort of evaluate other techniques against. And it's pretty flexible. You can have nearest neighbor 1, 2, 3. You have a lot of choices in how you define distances. You can do variable selection. It also gives you probability estimates. Of course, not nearest neighbor 1, but nearest neighbor 3. If you go back to this example here with nearest neighbor 3, the probability estimate for this point would be 0.667, right? Because 2/3 of the 3 nearest neighbors are plus. So you also get some sort of probability estimates out. You could use those to make an ROC curve if you wanted to compare it for a range of values. So it's sort of a very nice, simple classifier that you ought to think about when you're comparing classifiers, and you ought to have it in your sort of toolbox. OK, so we did that. Yep, that's all I wanted to say about the nearest neighbor classifier. Any comments about nearest neighbor classifier? Questions? OK, so it's a pretty simple classifier. It's something you can always try on the data. The next thing to talk about is a more complex classifier. This is the support vector machine. This is talked about in section 5.5, which starts on page 256. And motivation for these are the following, right? If you think about your two classes being linearly separable, okay, so why do I care about linear boundaries? Well, a lot of procedures look for linear boundaries. So for example, logistic regression, you would think of a linear boundary. Even linear discriminant analysis would use a linear boundary. Now, with logistic regression on this data, okay, any line that separates the points would sort of be perfect, right? If you think about misclassification error, right? If I'm trying to separate these points with a line, any line I put through them gives me 0 misclassification error, right? That line gives me 0 misclassification error. That line gives me 0 misclassification error. The question is, how do we choose the best line when there's infinitely many lines that all give me a perfect fit, right? They're all perfect. What's the best one? What's the most perfect of all the perfect ones, right? Well, you sort of think that, like, intuitively, this diagonal line looks like it's doing a lot better than this line, even though they're both doing a perfect job of classifying all the points. Here I sort of have a couple close calls, right? Whereas here, the call is not as close, I guess I'll say. So in that sense, it looks like the diagonal line is doing better. And to formalize that, what the support vector machine is looking at, or more specifically the maximum margin separating hyperplane, is looking for the hyperplane, or in 2 dimensions it's just a line, right? 2 dimensions line, 3 dimensions plane, higher dimensions hyperplane. It's looking for the line that gives you the largest margin, where the margin is defined as the distance between the 2 parallel lines that you can draw on either side of the line and still have perfect classification, right? So from the diagonal line, I can go this far in this direction and the same distance in the other direction, and that's my margin, right? And so actually that's 2 times my margin. The margin is defined as this distance, which equals this distance. That is your margin. Whereas this other line here, the dotted line, you see the margin is just not very big. It does a perfect job in terms of misclassification error, but in terms of margin, it does not do a perfect job. So you can sort of think of margin in this case as being a metric like when we were growing trees, right? The misclassification error may not improve, but the Gini index might improve. Same thing here. Both of these give you 0 misclassification error, but one of them has a larger margin. So if we search for classifiers that have a larger margin, it'll sort of point us in the right direction. Why does it matter if they're both doing a perfect job? It matters because when we get new data, the one with the larger margin is going to generalize better. Okay, it's okay, I do a perfect job on the training data, that's no big deal, but the large margin hopefully will do a better job on new data. Okay, so there's some notation your book uses. I won't get into this too much, but this is pretty standard, right? So you sort of think about, a line in the equation ax plus by plus c equals 0. That's all this is, right? w1 times x1 plus w2 times x2 plus dot 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 plus the intercept equals 0. That's the equation of your line, or in higher dimensions, your hyperplane. Okay, the 2 hyperplanes are the 2 lines on either side. Well, this is w dot x plus b equal -1, and this is w dot x plus b equal +1, right? You could replace this by any constant, but let's just scale it to be 1 and -1. Okay. In that case, then, the margin becomes 2 over the norm of w squared, right? That's going to be this distance here if you go through and do the geometry and the math. And then you also have to get every point right. So it turns out that if you're on this side, right, because this is the +1 line, all these points sort of have higher x values in that sense. So they all become greater than or equal to 1. And all these points have lower x values in the sense of the dot product with w. So they all become less than or equal to -1. So on this line, I'm equal to 1. If I move off in that direction, I become strictly greater than 1. On this line, I'm -1. If I move off in that direction, I become less than -1. Okay, so this is sort of the notation we'll use for the problem. And now formulating the maximum margin hyperplane becomes simply a convex optimization problem, right? Because you want to maximize your margin, which is, you want to maximize, right? So, sorry, the margin was this thing, right? You want to maximize this. So that's 2 over the norm of w squared. So that's equivalent to minimizing the reciprocal. And then you have the constraints. The constraints are basically, if you're on that side, your dot product plus b has to be bigger than or equal to 1. If you're on the other side, your dot product plus b has to be less than or equal to -1. So we have a quadratic objective function with linear constraints. So we're doing convex optimization, and we can use Lagrange multipliers, and you can sort of turn the crank, and you can solve this problem, right? Quadratic criterion with linear constraints. So no problem for optimization. Now, the question comes up when you're trying to apply this thing in practice, what if the problem is not really linearly separable? right? In this case, I have 1, 2, 3 green guys that are on the wrong side of the margin, and 1, 2, 3 red circle guys that are on the wrong side of the margin, right? There's no line I can draw through this data that will separate it perfectly. So you can sort of allow for that, and that's allowed for by introducing some slack. So each one of these guys, excuse me, has a slack value, and so you add those guys up and you give yourself a penalty every time you have one of those guys. Okay, and that C is a parameter that you can tune. The software has a default value, but you can change it. I'll show you how to do that. And so now you're trying to minimize this thing subject to your own constraints, but now I don't have to be strictly greater than or equal to 1. I'm greater than or equal to 1 minus some sort of penalty there, and same thing here, I'm less than or equal to 1 minus whatever the extra value I had to add on, right? So for this guy, I have to sort of add on a value to make him actually on the right side. So that exactly is my penalty term there. So you just introduce these slack variables, and you can still do the optimization. You just give yourself a penalty for every one of these guys that winds up being on the wrong side, and your penalty is proportional to how far he is on the wrong side times some cost value. Okay, so that allows you to sort of deal with problems that aren't linearly separable. There's another trick that allows you to deal with problems which are not linearly separable, and that is that you don't have to use just x1 and x2, right? What if you say, you know, even if I drew a line through this data and allowed slack, a linear boundary isn't really the right thing in this space, right? Really, I want some sort of nonlinear boundary. So this is the same trick you use in regression problems, right? If you're doing simple linear regression, there's no reason you can't do simple linear regression on x1 and x1 squared. So it's not really linear in terms of x1 and x2, but it's linear in terms of whatever transformations you define. So you can just sort of define any transformations. If x1 and x2 don't do the trick, let me try x1 squared and x2 squared, right? It's still linear in the space of x1, x2, x1 squared, and x2 squared. So you can sort of make it linear in this higher dimensional space by just making a higher dimensional space by taking transformations, right? So here they use x1, it looks like x1 plus x2 to the fourth, and actually in that space, you can actually separate it perfectly. So you can always map up in some higher dimensional space in order to get these things separable. In fact, there's actually this kernel trick that you can use where you can actually map up into an infinite dimensional space. How does that work? Well, the whole sort of, you know, all the optimization is in terms of dot products, right? And so dot products, well, those are just sums, and sums can converge even if they have an infinite number of terms in them. So there's some spaces you can map into that are infinite, and when you talk about like radial basis function, things like that, you're actually mapping into infinite dimensional spaces. Now, it's hard to draw those and sort of see, but if you look at the math, you realize you're just taking dot products, and so there's no reason you need a finite number of dimensions.
Is there any sort of guidance as to what functions to try out?
So everyone seems to like radial basis functions, but you can, you know, people write papers about this. I will tell you that the default in the package I'm going to use is not the linear basis function. It is to take this radial transformation. Do you have a...
So I'm just wondering if you still use the same metric. Like, do you try to map back and use the metric from the original space, or do you?
No, you work in this warp space, right? And so there's this reproducing kernel Hilbert space that you work in and sort of map everything to that space.
And isn't it also possible that you can overtrain just by, you know, casting about until you found just the perfect function?
Right. Yeah, so I mean, the sort of the overfitting problem and the crystal dimensionality are something people argue about with these things. And there's a lot of theory that goes into generalization in terms of the margin. And there's a lot you can read about. Back in the 90s, these things were sort of very, very hot topic. They're still well respected as a technique that does effective classification. I'm not the best person to speak about them. They do come more from a CS perspective than a statistics perspective. So that's another reason I'm not the best person to talk about them. But I will say sort of this, and that they are a very effective technique, and I'll sort of illustrate that for you. Okay, other comments about what I've said so far about support vector machines? Okay, so let's, yeah. Yeah, it is, really. So, I mean, statistics, you know, we had logistic regression, we had linear discriminant analysis, but support vector machines were not invented by statisticians.
Oh,
so,
just not invented, but do you think that's actually more useful in the CS application?
So, I mean, the one thing I'll say is they tend to do really well for problems that are deterministic, right? And statisticians tend to be a little bit more attractive to problems that aren't deterministic. Now, arguably, though, you know, both, you know, techniques can work well. It's a matter of where they come from, right? So I'm not saying that they're not effective. I'm just saying that sort of their background is from CS. And so if you talk to an average statistician, they might sort of have some opinion about them. You talk to the average person from doing machine learning, they might say something different about them. So I don't want to say too much because I'll show my hand or something like that. But anyway, they're coming more from a CS background than a statistical background. But in terms of solving problems, I mean, they're a competitor, right? They're a competitor to logistic regression. They're a competitor to anything else you can think of. Okay, so here is in R. So I know there's other packages. This is the one that I was familiar with, the E1071. This is sort of maybe an older one than some of the ones that might be around now. I know there's this SVM Lite that people like to use. But anyway, this E1071, so what does it take here? Basically, you give it, I don't have the call up here, but, oh yeah, I do. So you give it X and Y. By default, the kernel is the radial basis functions. You can override that by specifying the linear kernel. And then you can see there's a lot of other values here. The cost by default is set at 1, which is actually a pretty low value of cost. If you play with this on some toy examples, you'll see that it won't even separate them when it easily could separate them by line. So you often want to crank up the cost. But again, that's sort of a tuning parameter, and there's some other tuning parameters. If you look at this thing on something like the sonar, so if you remember with the tree, we had like 30% accuracy. With nearest neighbor 1, 30% misclassification error. With nearest neighbor 1, we had 21% misclassification error. With this thing, it turns out I can actually do a lot better. So install the package, I read in the training data, I make y a factor, and then the call here, I'm just going to do the default. SVM x comma y. Okay. Once I do that, it gives me a separating hyperplane. Okay, so I have this fit object that gives me a separating hyperplane, and then I can predict using the fit object, so I can predict the fit for x. So this would just be misclassification error on the training data, which I don't care about too much, but just so we can compute it, I will do that. And you'll see that on the training data, okay, it actually gave me 1.5%. So I actually know that nearest neighbor 1 gave me 0%, so 1.5%. Well, that means that it's actually not separating all the classes perfectly because of that. It has that slack variable in there, and the default value of cost is not forcing it to separate perfectly. It's getting, I guess, what is this? This is probably 0.015 times 130 points. It's getting all but 2 of them, I guess. It's separating all but 2 of them perfectly by default. Okay, but again, misclassification error on training data is not what I care about. I care about the test data. So to do that, I'm going to use the same object, but when I do predict, I'm just going to predict for the x test. Predict for the x test as opposed to the x. So the same object that I gave x before, I give x test. And when I do this, I can see how well it performs on the test data, which it hasn't seen before. So fit did not see the test data, it just saw the new data, and you see 12.8% for SVM. 12.8% for SVM. This, if you know much about the sonar data, if you ever read a paper where they're comparing different classification algorithms, that's about as good as you're going to do. 12.8%. After this, any improvements arguably are sort of in the noise and depends on how I split the data into training and test. Sometimes to get more accurate measures of this, people will do repeated partitionings into training and test, but you're going to be hard pressed to beat anything around 12.8% with any classification technique you use. Some of the other techniques I still have to show you will also be competitive to this, but if you just sort of think about it, we started off with like 30%. Everything we did with those decision trees, all we really got out was something that was getting like 30% misclassification error, which is really pretty bad compared to 12.8%. Nearest neighbor technique, I was able to do 20%. You can do a little bit better if you change, I think, to nearest neighbor 2 or 3, do a little bit better. But you don't get close to the 12.8% that you get with SVM. So whether or not you sort of like the theory and the development of the SVMs, they are very competitive in terms of classification, which is really, in the end of the day, what you're after. Classification accuracy on new data. SVMs do quite well. This one did pretty well, without me even tuning any of the values. So I think that's all I wanted to say. Any comments on this example?
How well would it do the linear kernel?
Let's try it. So let's see, what do I have to do? So the question is, how well would it do with a linear kernel instead of the default one, which is radial basis? So let's see. If I just change this thing and I say, comma, kernel, equal linear. Okay, and so let's see. On the training data, I have the same error. I did change it, didn't I? Kernel equal linear. Yeah, okay. And on the test data, how well do I do on the test data? Well, bad. 37%. But, you know, I didn't tune it, right? And so presumably those defaults are set to be good defaults for, you know, the radial basis function, which is the other default. So arguably changing one of the defaults without changing the others is, you know, I'm half tuning it, so it doesn't really work that well. Okay, I will show you an example with the linear basis function in a second. Any other comments, questions on this example? So far this is the best thing we've seen on the sonar data. Okay, let me show you sort of a little two-dimensional toy example. I actually gave this as one of the homework problems just so you can visualize it. So here's just two-dimensional data, right? x1 and x2, and I made the first 5 negative ones and the next 5 positive ones. And I just said, let's fit the SVM with kernel equal linear, so we can actually see the optimal separating hyperplane in the original space. And I cranked up the cost value. If you don't set that really high, it actually doesn't give you the optimal separating hyperplane. Okay, so we're going to fit this two-dimensional data, and I want to give a plot of the resulting classification rule. So you can see there's sort of a little bit of a hack, but it's sort of a cute trick I did to make that plot. So the first thing, I haven't showed you this syntax before. So I can read x in. I just read it in as a matrix. I just go 0, 0.1, 0.8, 0.9 like that. And then I say by row equal true, number of columns equal 2. So this will actually read in the x data. And then the next thing, I give it y and make sure it's a factor. So let me just sort of convince you that this is reading in the x data. Let's see. Okay, so there's x, right? That's x, that's the matrix, 2 columns, two-dimensional problem. Then y is just a factor, 5 negative ones and 5 positive ones. So do that, and I have y. Okay, now I just want to sort of look at the data. So I'm going to make this plot here. And I think this plot isn't too mysterious what it's doing. I used a really big character just so we can see it. x1 and x2, I've showed you that before, how to put the subscripts on. So basically, this is the training data. I don't know, is there anything I didn't tell you here? So a couple tricks I used here is that CEX equal 2, that makes the really big points. CEX is the size of the plotting symbol. Color equal 2 times as numeric y, right? So color, we usually say red or blue, but you can give it numeric arguments. I think 0 is black, 1 is red, I think 2 is blue, something like that. So as numeric y, this will default to numeric, and so just by multiplying it, I think that way I get, what were the colors here? 2, anyway, doesn't matter too much, but red and blue. So I guess 2 times as numeric y gives me 2s and 4s. So I think, yeah, so that's why I get the red and blue. Those correspond to colors 2 and 4. And then CX equal 2, I showed you that. Okay, so that just gives us our plot. The next thing I'm going to do, of course, is to fit the SVM to x and y with kernel equal linear, and I'm going to crank up the cost. So this will fit the optimal separating hyperplane in the original space. The cost will be really big, so I'll make sure that it goes through all the points and gives me a really large margin and doesn't sort of allow for any slack, because if you look at the data, right, I ought to be able to sort of do a good job through this data, you know, if I come somewhere through here. I ought to be able to, these are sort of the 4 points that I need to avoid. I actually didn't talk too much about that. One of the cute tricks as you're fitting the SVM is that it turns out there's a lot of data points that don't really matter at all. And so in this case, you start to see these 4 points are going to be really, maybe this one too, but certainly no reason to worry about those points. Okay, so, and that's where this term support vector comes from. Anyway, so I ought to be able to do a really good job of fitting a hyperplane or a line right through there. So that's what I'm going to do here. Fit stores SVM kernel XY kernel linear cost 100,000. So I do that. And by the way, if you look at the object fit, you can sort of see that there are 3 support vectors and that it did use the cost I gave it and things like that. Okay, then what else do I want to do? I want to sort of see. So now, okay, I fit a SVM. I can use that to predict, but but I don't want to predict just for 1 or 2 points. I want to see what this decision boundary looks like. So I'm just going to create a whole bunch of random x's, right? Random uniform 200,000. This will give me 200,000 random uniform x's, random uniform defaults to 0, 1, which is where this data lives. 2 columns, and just do by row, that doesn't really matter. So I'm just getting two columns of 100,000, just a whole bunch of x's. I'm just trying to fill up the space so then I can color it in. How am I going to color it in? I'm going to call points on the big X. Color, I haven't showed you this one before. Color can be RGB. So if you don't like any of the colors that R gives you, it gives you like 300 of them, but you can just specify your own color using RGB. Red 0.5, I did blue 0.5, but then red 0.5, green 0.5, but then the blue, I'm going to do an as numeric predict fit big X, right? So predict fit big X, this is going to be the predictions from the support vector machine for this huge X matrix I just made. And when that equals 1, this is going to be 1, and so my blue is going to be 0.2 plus 0.6, 0.8. When this is false, this is going to be 0, and so my blue is going to be 0.2. So this will give me 2 different colors depending on the prediction, and then the plotting character is 19. Then the final problem is that once I do this, it covers up my original data. So points always puts on top the last thing that you made. So then I just recall the original points command to put my training data back up there. So let me do this, and I'll show you what happens with that much of it. Might take a second because there's 100,000 points, but you can see, oh, I should have had that window on top first. Well, there you go. You see it just basically colored in everything blue that was classified as blue and everything with this greenish color that was classified as red. And I've covered up my original training data, but I can put it back if I just call points again. Of course, there's more smooth ways of doing this plot, but this is sort of an easy way to do it. And points there you see. So the 100,000 points just filled in the space, and I color them, and then you can see here's your linear boundary given to you by SVM. And it turns out if you actually look at these 2 points, and this is what I gave the students on the homework, if you actually look at these 2 points and compute the distance to this line, it turns out to be the same, and of course that's the largest margin you can get. Any other line you drew through that data, there would be some point that was closer to it than these 2 distances are. So of course the SVM here you can see is doing what I said it would do. Of course to get it to do that you do have to trick it a little bit and say kernel equal linear and make the cost really big. But that's what it's doing. And so in 2 dimensions I can see what it's doing. In 60 dimensions, for the sonar data, it's hard for me to see what it's doing, but what really matters is that I get 12.8% misclassification error, which is very, very, very competitive. Okay, so I think all I wanted to say about that, here's the picture up on the slide, the same as the one I just drew. That's your optimal separating hyperplane as computed by the SVM in R. Okay, so I think that's all I wanted to say about that example and all I wanted to say about SVMs in general. Question?
What do you get with the small cost?
You don't, okay, so it's interesting. With a small cost, it goes pretty close to one of those points. So the question is, what do you get with a small cost? So let's see. So I'll just do the cost of 1, the default, and show you. So cost of 1, and then do everything again here. Cost of 1. Sorry, it's not on top. I should just make this window a different size. Up. So it looks the same, right? But it's not because, oh, where's my points? It's not done yet. Oh, I didn't hit return. So, right, see, this is really, really close. That's not the optimal margin, right? You can do better than that. And so it separated them, but it didn't, it didn't get that one really, really close. And also, if you're curious, I guess the other question to anticipate is, what if I don't give it a linear kernel, right? What if I just do the default? And of course, then you get sort of this curved boundary. And look at this one. Here, let me be smart and let you see it color in. So here's the default. The default is to use a radial basis function, which winds up being a curved boundary in the original space. Okay. The other thing you can play with, which is kind of cute, I won't do it now because I'll probably mess it up. If you move one of these points so that it's still linearly separable, and you ask for the linear kernel with the cost of 1, you will actually get solutions where it could have found a perfect separation and doesn't. which is kind of curious. So that's why I'm saying that that cost default value seems pretty low, because often it can find a perfect separation and won't. Okay. I mean, that's just sort of, if there exists a perfect separation, you would think it would find it, but by default it won't if the cost is 1. Okay, other questions, comments about SVMs? So again, I'm not the perfect person to tell you about these things. They come from machine learning, which isn't really my background, but I've encountered them, as competitors to sort of other classification techniques I've studied. And the bottom line is they do pretty well.
Does this method have some kind of convergence tolerance?
Yeah, if you look in the help, there's sort of, I think it has to do with, where do they go? It's either this new, or there's another tolerance. I think it's probably the tolerance, right? Either the tolerance or the epsilon or some combination of both. So you can sort of specify how much you want.
So it seems like the biggest weakness of the SVMs is that they completely ignore a lot of the data points that are close to
Well, so you're saying that, so the question is, it seems like a weakness that's ignoring some of the data points, but some people have argued this is a strength. So it's true, whether it's a weakness or a strength.
Well, it seems like some of these could really, suggest some sort of a trend, or like, if they were sort of arcing in some direction, but you just
Right.
didn't see enough of them to really
Right.
see where it was going.
Yeah. Yeah, I mean, your intuition sounds logical. I mean, people will argue this both cases, but people that are proponents of SVM say this is a great feature, that it doesn't have to use all the data because only some points matter. So.
You think of it as sort of like a median, which basically ignores how far away from the median those data points.
Right. So that's Charles' point. So
It strikes more of a presidential race. Most states don't matter because you focus on the few key ones.
Right. Yeah. So I mean, yeah. So there's a lot to read about these things. There's a lot of literature. It's still an active research area. Actually, I say that they come from machine learning, but the group at Stanford is actually pretty active in studying these things, and they've done a lot in terms of this regularization parameter where they actually let you vary it and find sort of the entire path, as opposed to just, let me put in one cost and do it, let me put another cost and do it. They actually have a solution where you can vary the cost and trace the whole path along. And there's a lot of interesting research in this area. It's not really my area, but you should know it's a very effective classification technique. Okay, any other comments, questions on SVMs? All right, so the last thing in Chapter 5 is, we did this. Last thing in Chapter 5 is to talk about ensemble methods. This is Section 5.6. Now, ensemble methods is a pretty big umbrella, but in general, these methods your book describes as improving classification accuracy by aggregating the predictions from multiple classifiers. So the most obvious way to do this is simply averaging a large collection of classifiers. And if these things make errors somewhat independently of each other, and we take the majority vote, we can do quite well. So for example, let me just motivate this. And oh shoot, this is the same motivation your book uses. So imagine that you have 5 classifiers, and each one is correct about 70% of the time. Okay. Also imagine that these classifiers are completely independent of each other. Now, of course, when we're doing these ensemble methods, we're not going to get complete independence, but you should sort of think about what happens if you were able to get complete independence. And then you take the majority vote. How often is the majority vote going to be correct? So this is sort of the wisdom of crowds thing, right? If people function independently, and they're all functioning independently, and they all have some accuracy rate, the overall accuracy rate of the majority vote is going to be much higher. And specifically in this case, if each one is 70%, and we're looking for the majority vote out of 5, well, of course, if all 5 are correct, 1, 2, 3, 4, 5, that's just going to be, 0.7 to the 5th, okay? So that would count. Also, if just 4 of the 5 were correct, okay? So you could do this, and you could actually do this, of course, binomial distribution here. You could do this 5 different ways, right? Correct, correct, not correct, 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 plus probably correct, correct, not correct, 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 plus the last one, not correct, 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 correct. Okay, and so that's going to be, there's 5 of them, and they're all 0.7 to the 4th times 0.3 to the 1 power, right? Okay, and then finally, if I'm doing majority vote, I need 5 out of 5, 4 out of 5, or 3 out of 5 would do it, right? Things like this, not correct, 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 plus all possible reorderings of that, and you can actually figure out this is going to be 5 choices times 4 choices divided by 2 should be 10 choices. So 10 ways of writing that times 0.7 to the 3rd times 0.3 squared, right? So this is simply the binomial distribution. You're probably used to seeing this probability x equals n factorial over x factorial n minus x factorial. That's the number of ways of arranging x objects in a sequence of n things, times the probability, which is just going to be whatever the probability is for x successes, times 1 minus p for n minus x. Now, of course, the whole point to this is that we're assuming, I said, perfect independence, right? They're completely independent of each other. But if I figure out this number, and this number, and add them together, that's going to be my probability using the binomial distribution, which of course is assuming complete independence. So let me just do that. So let's see here. So we have the chance that all 5 are correct, which the majority vote would be correct, or 1 is wrong and 4 are correct, which can happen 5 different ways. And then I could have 2 of them wrong as long as the other 7 were correct, which can happen 10 different ways. So it's a high probability. So where's 0.7? 700, there we go. 0.83692 is the answer here. 0.83692 compared to 0.83692 compared to the original probability, which was 70%, right? So if you have 5 people that are 70%, they're correct 70% of the time, they vote independently of each other, their majority vote is going to be correct 83 or 84% of the time. So this is sort of the whole motivation behind some of these ensemble methods. Is if I can get a whole bunch of different independent classifiers, get them to vote, take the majority vote, I can do a lot better, right? So for example, you might say, let me fit, a whole bunch of different SVMs and take the majority vote, or let me fit a whole bunch of different trees and take the majority vote. Now, those trees aren't going to be completely independent, but if they're somewhat independent, if they're somewhat uncorrelated, you might be able to improve your accuracy. So that's the motivation here. Now, of course, this value of 0.83692, I showed you doing it sort of this way. There's, of course, a built-in binomial function in R, and you give it, well, I'll just show you the help on it. The arguments you give it are, the 5 there is the total number, the 0.7, of course, is the probability, but question P binom, is that it? Okay, so by default, it's giving you, so here's the binomial distribution, right? This is this n choose x thing here, p to the x, 1 minus p to the n minus x. By default, of course, it's going to give you the less than or equal to probabilities. So that's why I did the 1 minus, right? Because I want the majority vote correct. So if the probability of correct is 0.7, then 1 minus 2 or less. 1 minus 2, 1 or 0 will give me 3, 4, or 5, which is the probability I'm after here. Okay, so you can do that. And the very next slide says, well, what if instead of 5, you have 101? Now, I picked an odd number just because, what do you do if you have a tie? So let's just 101. So that way, if I get 51 or more of them correct, and each one is 70%, I should do pretty well. And so that will give me the answer there. And just to compute this thing you see here, Control C, if I had 101 of them, I would be correct 0.999987. Like 100% chance almost of being correct by taking the majority vote from 101 independent classifiers that is each correct 70% of the time. So again, this is the motivation behind ensemble methods. If I could grow 101 trees and they only had 70% accuracy, which is what our trees had, but there was 101 of them that were completely independent, I'd do almost a perfect job every time. Now the complete independence, of course, is the catch because you're not going to get that. But the whole motivation behind ensemble methods is to try and get as much independence as you can with regard to bagging and random forests. That's sort of the motivation for those. Boosting is a little bit different, right? So it's not obvious that we should combine that into this sort of collection of ensemble methods, but this is sort of the organization your book uses. So we'll talk about these next time, just to give you sort of an overview. What bagging is doing, I mean, the whole question is, right, how am I going to get these 5, or how am I going to get these 101 independent or somewhat independent classifiers? Well, with bagging, what you do is you take your classification algorithm, but you train it on different samples from the same data. So you build different classifiers by training on repeated samples with replacement from the same data. So if I have 100 observations, let me sample 100 of them with replacement. sample another 100 with replacement, another 100 with replacement, train my classifier on each one of those subsamples, and then average over them. Of course, those aren't going to be independent because they're trained on a lot of the same data, but if they're somewhat independent, I can improve accuracy. Okay, random forests, those are, so bagging works, any classification technique. You can bag any classification technique because you just take samples from the training data. Random forests, the name forest sounds like a tree, and in particular, random forests are dealing with trees. They basically average many trees. How do they grow the trees? Well, they don't sample the data so much as they sample the attributes. So as they're growing the tree, at each node, right, when we grew the trees last time, at each node we had to select which attributes on which we were going to split. What random forest does, and it does different randomization techniques inside there, but one of the things it does is at each node, instead of taking the best variable to split on, it takes a random collection of the variables and chooses the best among those. Or sometimes just chooses a random variable and takes the best split on a random variable. And so then you get a whole bunch of different trees, you average those, you take a majority vote. That's random forest. It's a very, very effective technique. It's rivaling SVM and other techniques. This is Leo Bryman's invention. If you had a chance to meet Leo Bryman before he passed away a couple of years ago up at Berkeley, he's a really, really smart guy, and he invented these things, and to this day they're still a competitor to a lot of the other techniques that have a lot more theory and things that go with them. I mean, he developed some theory about these. He gives bounds based on the correlation and the accuracy, but in some way there's sort of an ad hoc method that just tend to work really well, and it's because he understood why trees weren't working well. He understood that trees had too high of a variance and that you needed to sort of stabilize them, and the way to do that was to average them and introduce randomization. So these are a great technique. I'll run through those next time. And then the final thing to talk about is sort of one of the areas that I like, which is boosting, which it's still combining trees, but it's not doing it so much by random as it's upweighting data which you got classified incorrectly, right? So you grow a tree, you get some observations right, you get some observations wrong, you go back to the ones that you got wrong, you upweight them, the ones that you got right, you downweight them, you grow another tree, you combine those two trees together, and it's a very aggressive procedure because it keeps upweighting the data that it got wrong, but you can start with very small trees, and by upweighting the data that you got wrong, you can actually, from very small trees, get a collection of small trees, which can learn sort of any complex decision rule you want. Okay, again, that's just the training data. Everyone can do well in the training data. It turns out, though, that these things actually, just like SVM, just like random forest, perform really, really well with regard to new test data. And these are a little bit mysterious. People tend to disagree on why boosting works so well. But we won't get into too much of that except to show you that it does work and to show you what it's doing. So I'll talk about these three procedures next time. And we'll also talk about a little bit about clustering next time. In particular, I'll go through the k-means algorithm. So that's all I had today. Any comments before we take off? Okay, so again, Friday will be the last day, and I'll see you Friday.